Alright, first off, please excuse the sound of the vacuum cleaner that you hear off in the distance. So what we're looking at here is finding the intersection point of two vector lines. So just a quick review of some concepts. In 2D, are two different possibilities for two lines is they could be parallel to one another or they could intersect. In 3D, we can have, of course, two lines that are parallel. Okay, so imagine hold up your arms right now in front of you in such a manner where they are parallel to one another. Okay, so that's a possibility. Now take your arms and make them intersect with one another. Okay, and then take your arms and put one on top of the other in such a manner where we say they are skew. That means they're not parallel, but they're never going to intersect either. So skew refers to lines that are neither parallel nor intersecting in 3D. Okay? Alright, so here's an example where we were looking to find the coordinates of where these lines intersect. So we're given two lines, two equations. We have r sub 1 representing the first one, and then r sub 2 for the second one. Notice that we have different scalars. We have a t and we have an s. So let's first attack this graphically. So it's just helpful in the beginning to get a visual of what's happening, to find the intersection point that way. But then, of course, if we are in 3D, this is not going to be a very good option. So we'll look at doing it graphically, and then the bigger one that you have to keep in mind is how to do it algebraically. So suppose we're talking about the point 2, 3. So we know we have that point, and I'll label this 2, 3, and we know that its direction is 5, negative 1. So to the right 5 and then down 1. Okay, so our first one here would look like this. So I'll just label this r sub 1. And of course, if we were to find the coordinates of this next point from 2, 3, if we were to add 5 to the x, we get 7. If we subtract 1 to the y, we get 2. All right, we can continue to find more points, but we'll just keep it at that for now. Now, if we were to graph R2, let's plot the point 1, negative 6. So let's say that's down here. Okay, so here is my 1, negative 6. If I apply my direction vector of 3, 4, it means I would have to add 3 to the x and then 4 to the y. So my new point, if I were to do that, would be 4, comma, negative 2. Okay, so I'll put that point right here. And then from that point, and again, the direction vector is 3, 4, so we're going to be heading this way. From there, if I were to add 3 onto the 4, I'm going to get the 7. And then if I were to add 4 onto the negative 2, I'm going to get that positive 2. So we could actually see right where they intersect. Okay, so the coordinates here would be coordinates would be 7, comma 2. All right. And so again, we were able to do this graphically, but if we were in 3D, we need a better way. So if we were trying to figure out where these are equal to one another, what we're going to do is we're going to just set these equations equal. We're going to just drop the r equals part. We're just going to set the rest of it equal. Oops. So we would have 1, negative 6. So we have an equation here with both a t and an s in it. So what we're going to do, and we saw something similar before, we are going to split apart these two vector equations. We're going to first write an equation with just the top layer of numbers, so just the x components, so 2 plus, now if I were to distribute that t into that vector, we would have a 5t, and then that would equal 1 plus 3s on the other side. And then down below, okay, so notice now we have two equations with two unknowns. Our two unknowns are s and t. So what we need to do is solve for one of these variables. And so what we tend to do is we use elimination method. Notice how everything is lined up perfectly for us. So notice we have a 5t and then a negative t, and then we have a 3s and a 4s. If we want to eliminate our t's, I can multiply this equation by a positive 5, because that's going to give me a negative 5t, which will cancel out with that other t. So I need to now distribute this 5 to all of these terms. So I'm going to have 15 minus 5t is equal to negative 30 plus 20s. So notice how I distributed that 5 to all of the terms. So I'm now going to just put a line through this. Don't scribble it out completely. We want to still be able to see it. But I'm now focused on just using these other two equations. Okay. All right, so since we're doing elimination method, that means we are going to be adding these other two equations. So I'm going to be adding the 2 and the 15. I'm going to get 17. The 5t and the negative 5t, they're eliminated. That's why we multiplied by 5 so that we would have that opposite relationship there. Then I'm going to add the 1 and the negative 30, so negative 29. And then I'm combining the positive 3s, positive 20s, so we have positive 23s. So from there, just solve this equation. So that would give us s equals 2. So we found one of our scalars. We found that up here the s is 2. So look what happens if we were to put a 2 in there. So we would have, let me go down below here. I'll do it up top. We would have the 1 negative 6 plus, if I put the 2 in there, that if we multiply it into that vector would give us 6, 8. And notice how the vector would be 7, 2. So sometimes the question may ask for the position vector of where they intersect. So you can see that that would be the 7, 2. Or in this case we wanted the coordinates, so 7, 2. Now one quick note, notice how we never found t. We never solved for t. If we did solve for t, if we go back to one of our equations from when we did elimination method, how about the first one, 2 plus 5t is equal to 1 plus 3s, we found that s was 2. So go ahead and solve that equation for t. So if we do that, we end up with t equals 1, and then if we went back up here and put a 1 in here, notice how we would get the same thing of 7, 2 for that vector, okay? And confirm it graphically. We only had to make one movement on this R1 equation, which was going in this direction. We only needed to apply one scalar, whereas with the other one, which was heading this way, we had to apply 1 and then 2 scalars to get that intersection of 7, 2. So you don't have to find both scalars, but you really just need one in order to find the intersection, but it doesn't hurt just to check. Okay, last example. This time we're looking to find the position vector of where these two lines intersect. Notice it's in 3D, and this time we're not going to be doing it geometrically or graphically. Okay, so we're just going to simply start by setting these two lines equal to one another. And notice how we don't have r equals, we have capital L sub 1, that just stands for line 1, and then we have line 2. So let's set these equal to each other. Okay, so now from there, we're going to split it apart. Now in 2D, we had two layers, or two components, an x and a y. Well, now we're going to have 3. So that means we're going to have 3 different equations when we set this apart. So go ahead and do that. Alright, so when we split these apart, notice that there's some zeros in here. So I put them in there as placeholders, but you really could just write nothing there, there, and there. Just kind of leave it blank if you wanted to. So the way we're going to approach this is we still have two unknowns, s and t, but we have 3 equations. Now sometimes you'll need elimination method, but here we actually don't need it, because if we were to focus in on this equation up top, notice that we could solve directly for s. Alright, you have 3 plus s equals 6. That means s must be 3. So we're very fortunate here because it's very easy to find one of these scalars, okay? And so from there, since we know they are going to intersect, alright, if they're asking you to find the intersection point, what's implied is that they will intersect. So we're going to throw 3 in for s, and if we simplify this, we end up getting, when we clean it up, the vector 6, 3, and 2, okay? So they're not always going to be this easy, but be on the lookout for those zeros because, like I said, you're going to end up with a nice situation where the t is gone in that one equation you end up getting s equals 3. Okay, so it's not necessary to find the other scalar t. As long as you have one, you're able to find where they intersect. Okay, last example here. This one's a little more complicated. So we're looking to find the coordinates of the intersection. So we'll start by setting these equal to one another, just like before. Okay, from there, let's split it apart. Okay, so from here, notice it's not as easy as the previous example because we don't have an s or a t completely eliminated in one of the equations, so we can't solve for it directly using one equation only. So the way we're going to do this in 3D is the same way we did it in 2D. What we're going to do is we're going to ignore one of these equations, and we're going to pair together just two of them, and we're going to solve using the elimination method. Now it doesn't matter which one you choose to ignore. Alright, so let's suppose that I want to make the decision to ignore this top one, and I'm going to just work with these two bottom ones. Okay, again, there's different ways of approaching this. And let's suppose I want to eliminate the s's. If I'm going to eliminate the s's, then down the bottom here, I have a positive s. I see above it a 3s. I would need to multiply by -3. Now I could have chose to eliminate the t's. If I multiply the bottom one by 4, that would eliminate the t's. So again, there's different routes that you can take to get the same answer in the end. So let's go ahead and distribute. So we would have 3 minus 3s equals -6 plus 3t. Now from there, we're going to add these. So I'm going to just put a gentle line through that equation so I don't look at it. I don't want to be tempted to add any of those numbers. So I'm going to be adding the 3 and the 6 and the 3. I'm going to get 9. These are going to be eliminated. And then equals. I'm going to add the 1 and the -6. That's -5. And then I have the positive 4t, the positive 3t. So that's a 7t. If I were to add over my -5 there, I get 14 equals 7t. So t would equal 2. Okay? And so I could take my 2, I can go up here. Alright, and I can find my intersection point. So if I do that, so when we clean it up, we have the vector 7, 9, -4, which, remember the question wanted the coordinates, so I'm just going to take that and turn it and write it as an ordered triple. So this would be where those lines intersect in 3D. Now, if these lines were skew, meaning one is on top of the other, if a question said determine if there is an intersection point, what you would have to do is you'd have to find your s. Okay, so let's go back to these two equations that we used. Alright, we know that I'm going to take the one that just has a plain s in it. Alright, and I'm going to substitute in my s value, which I found. No, we're going to try to find s, and I'm going to put in 2, which I found for t. So that will enable me to solve for s. So I would get s equals 1. Okay, and so notice how if I put a 1 in here, I would end up with the same numbers of 7, 9, and -4 if you were to distribute that 1 through that second vector, right? Now, if they were skew, if we had to somehow determine or prove that they were skew, what would happen is we would have to then go to that ignore equation, which we said was this top one, and we would have to plug in these parameters. So we found that s was 1 and t was 2. Well, notice how we get 7 equals 7. That confirms that they intersect. If they were skew, this would not check out. Okay, so let's jot that down. So if they were skew, that would be false. Okay, you would have something like 8 equals 9. Okay, it would not check out. So the key to these 3D problems is to just focus in on two of these equations to make the decision that you're going to be ignoring one of the three. Doesn't matter which one. Okay, so you're just going to pair together two. You're going to solve it like a normal system of equations. Okay, but since we know that there is an intersection point, we don't have to bother checking it in that so-called ignore equation. But again, if we had to determine if there was an intersection point, then you would have to check it in that unused equation, okay, and then you would have to prove that it was true. But if they were skew, like I said, they would be false. Okay, goodbye.